This is a very important application of register where we can change the mode of operation. Okay, the mode of operation can be changed. We can design our own truth table. Okay, and accordingly we can get things worked out based on what we need for the combinations of A1, A0. Right. We saw what was a counter, and we saw as to where we are going to use these counters. And we also saw a new diagram called a state diagram, right? So state diagram tells us what is in the first state and then how it's moving on to the second state, or after first state, is it going to the third state, right? So it is telling me what state it is in right now, which means is it 000 or is it starting from 001? Okay, so we will solve a few problems based on these state diagrams, right? Then we even saw these binary ripple counters, right? We saw 4-bit, we saw the waveform as to how they come across. And the worst case here is from 111 to 000. Can someone tell me why is this called a worst case? Why is this called?
So because all the zeros which we have in the
Hmm.
different bits, they have to be converted to the ones individually, and every time we keep going, only like throughout the entire cycle, only one bit gets changed.
Good,
So it's a long process.
good. So which means there is no option for us to quickly jump to a particular state, right? So we have to wait one by one, one by one. So by the time it becomes high and then it goes to low, it's a huge, big process, right? So that's when we came across something called TPD, okay, propagation delay, right? Then ripple counters are also referred to as asynchronous. Then synchronous, what is synchronous? Can someone tell me? Synchronous. Shruti, what is synchronous? Shruti, you're there? Can someone answer what is synchronous? It is with respect to clock, right? So if we have clock, then we can call it as synchronous. So which means all these flip-flops will have a common clock, right? Okay.
Sir, I have one question on,
Yes, yes.
of previous topic. Like I was reading about the XS3 BCD.
BCD to XS3.
So yes, sir. So I just wanted to know how many parameters can we pass simultaneously in that. For example, I have a friend, he lives nearby, so he told me that that he is also in Bangalore college, so he's also learning it, digital electronic circuit. He told me that they are being taught 7 segments in which they can pass current by using BCD access of that diagram. So I'm just asking that how many parameters we can pass simultaneously.
Simultaneously, you can pass any number of bits. It's only just adding 3, right? It can be 2 bits, it can be 3 bits, it can be 4 bits, anything, right? To any number, you can just add 3. So which means this possibility is endless. Okay. It is not that we are working out only with 3 bits. No, no, no. We can, the possibility is n number. Okay. So it is like this, Nirmit. It is like, you can add 3 to 0. Okay. You can add 3 even to 100. You can add 3 even to 200. You can add 3 even to 500. Any number you wish to, right?
Okay.
So based on the number, consequently, your binary combinations also would change, right?
Yes, sir.
Yeah.
Okay.
Fine.
Thank you, sir.
Yeah, no problem. So we even looked into mod M counter and enable signals. Then how these load signals can be done. In fact, designing the digital circuitry is actually a talent. I can say. Okay, if you can just imagine or look at this circuit, it is so intelligently designed, wherein it can either take count or load, and the highest priority is given here to load, so that even though by mistake our count enable is given 1, the load values are taken up. That's because there's an inverter, and that's because there's a AND gate. So making use of the property of this inverter and AND gate here is special. Okay, fine. So I think now we have to start off with mod 10 counter. So when I say mod 10 counter, okay, we will have 10 states. Okay, we will have 10 states. So here, if you can count, okay, so it is starting from 0, okay, till 9. So which means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means how many states? 10 states, right? So that's why we call it as mod 10 counter, right? So there's a standard IC here, okay, wherein we have the outputs 0, 1, 2, 3, and our load, okay, the data bits 0, 1, 2, 3. And we have specifically for load and count, and then as usual clock. So the same diagram you can actually see here. Okay, this is the same diagram which we have here, wherein your data bits are towards your left hand side, your output bits are towards your right hand side, and then finally you have your carry output, okay, and your clock pulses. Can someone tell me what this symbol means? This symbol, what does it mean?
It's a edge triggered.
Sir,
What?
positive edge trigger.
Good. It's a positive edge triggered symbol. Okay. Suppose I have a bubble here. Okay. Then it is a negative edge triggered. Right. So there is lot of detail that is involved, when you look at each diagram. Okay. So it's not just a simple diagram. It's not just a modem counter. You just by heart the circuit. No, no, no. You have to analyze it, and then you have to understand. Right. So what do we do here? What do we do here? You have to look for values where Q0 should be high and Q3 goes high. So that is when I get 9. Right. So what I will do, I will just connect my Q0. Okay. Connect my Q0 and then connect my Q3 and then give these values to my AND gate. So whenever I give these values to my AND gate, as soon as these reaches 1, okay, as soon as these reaches 1, the output is 1 here. What happens? Load happens. Load means what? Load means what? This 0 will get inside. We are loading the values into the data bits. Understanding, students? So here, my Q3.
What was load, sir? Can you explain it once again?
Load is nothing but whatever value you want, you are just putting it. That is called load. Okay.
Like the input bit, sir.
Input bits. Loading the values. Loading the values means giving the values as inputs. Pushing those values. Pushing those.
Yes, sir.
Right. Okay.
And sir,
Now,
one more doubt in the input, sir. Why have they given 3 dots, sir? Like 0 and then 3 dots?
Where is it?
Sir, in the input for D0, D1, D2, D3, why have they given the 3 dots?
Sorted. See, when two wires are crossing, okay, if two wires are crossing like this, I will not say that they are connected. I will say that they are connected only if it is darkened. If there is a dark dot, it means these two lines are shorted.
Okay. Yes, sir.
Okay. Right. I think this concept is clear.
Yes, sir.
We can proceed. Fine.
Yes, sir.
So now you look at this truth table here. You have Q3 is 1 and Q0 is 1. So that's why what I'm doing, I am connecting this Q0 and I'm connecting this Q3 to an AND gate. So once it reaches 1, 1, so 1 and 1, this 1 will pass here and I will get my output as 1. So what is the operation? Load operation. So load means what? 0 will get inside. Why is it getting inside here? Because it has given load. Why are we putting 0? Because after 9, I want 0 to come. Okay. So that's the reason what I'm trying to do is I am trying to take this 0 and I am putting it in load. Is that clear, students? Is it clear or any doubts?
Like, why put 0, sir? We could just stop it from there.
See, it's a counter, right? It's a counter. So I just want a certain specific, what to say, states to be counted. That's it, right? I do not want it to go to the next state. So it is like a cycle. Understood?
Yes,
Yes.
sir.
Yes, sir. Yes, sir.
Yeah, it's like a cycle. So I just want that cycle to repeat itself. 0, 1, 2, 3, 4, okay, 9. Then after 9, again I want 0. I want it to come here. See, the idea is after 9, I want it to go to 0. Okay, so that is the cycle. And from here,
So, sir, basically, we are just making a circle. For
that's
example,
all.
repeating and then.
That's all. That's all. It's just a circle. Okay, it's just a cycle. Okay, so after this state, I want 0. So after 9, I want 0 to come. So I will load. So load, I'm giving 0. 0 will come, and then it will start counting. It will start counting. 1, 2, 3. It will keep going up as per the clock pulses. As I give clock pulses, the positive edge triggered pulse. Okay, the positive edge triggered pulse is here. So whenever it sees a positive edge, then it starts moving on to the next value. So are we clear with this?
And how do we control this cycle, sir?
How do we control the cycle? Stop giving the clock.
Yes. Okay.
So once we stop giving the clock, it's controlled. It's like, stop giving them food. Understood?
Yes, sir. Yes, sir.
It's like stop giving them food. So food is nothing but your clock here. Okay. I can say clock is like energy and this input is food. Okay. So if there is no energy, this circuit will not work. Okay. Fine. So suppose now I want, say, after 8, I want 0. What shall I do? After this state, I want 0. What shall I do?
So we need to short Q2 and Q0 to the load. Q2 and Q0.
Why Q2 and Q0? I will want to check. I will want to check only when Q3 is high, right? Only when Q3 is high, and I will check if 2, 1, and 0 is if all these three are 0, right? So accordingly, what I can do, I can check. I can connect this full thing to an OR gate, right? Full thing to an OR gate. So if I am getting an 8, okay, if I'm getting an 8, then directly I can connect that to load, right? So in that way also we can design. Or for example, if I want it to stop at 7, so Q2, Q1, Q0. So all these three I can connect and give it to AND gate. So AND gate's output will be connected to load. Load is connected to 0. So after 7, immediately it will give me 0. So wherever ones are there, those you should connect to AND gate. Understood? So here I
Sir,
had
can you
ones
just
at
explain
Q3.
the working of the whole thing once again?
Once again, okay.
The working.
See now Q3 is 1, right? So no doubt here with this. Q3 is 1 and Q0 is also 1. So what is this state? This is nothing but 9, right? And here I have 0. So which means totally how many states?
10 states.
10 states. Any doubt till here? Nothing, right? So after 9, I want 0. Just like how we discussed previously, I'm creating a cyclic repetition. So 9 means Q3 is high, Q0 is high. So Q0, I am connecting here. Okay, I'm taking one wire from Q0, and from Q3 also I'm taking a wire. So these two I am connecting to my AND gate. Okay, so AND gate is having a property where if one of the inputs are low, then what will happen? The output is low or high?
Low.
Low. So I'm getting a 0. If in case one of the values are 0. If both the values are high, then I will get 1. So 1 means load will be activated. So if load is activated, immediately zeros will come inside. Zeros will pass. It's like opening up these gates. So once the gates are opened, these zeros will pass through. Okay, and it will connect D0, D1, D2, D3. All these are fed with 0. So which means basically after 9, immediately I'm getting 0. So this will keep going on based on my clock pulse, my positive clock pulse, positive edge, rising value, low value to high value. Understood?
Yes, sir.
Fine. So can I move on?
Yes, sir.
Say for example, now I want 3. Okay, at this state. At this state, I want it to become 0. So what I should do? Q1 and Q0, I should connect to AND gate. Because only those two are high, right? Isn't it?
Yes, sir.
See, Q1 and Q0, only these two are high. So which means I should take those lines, Q0 is already there. So instead of Q3, okay, instead of Q3, I will take Q1. I will take Q1.
So they will be ANDed.
They will be ANDed. Once I get 1, 1 from there, then load will come, immediately 0 will come after this state itself. After this state only, I am creating a cycle. So in that case, it will be called mod 4 counter.
Yes, sir.
Understood? So 0, 1, 2, 3. So how many states? 4 states. So it will be called as mod 4 counter. Right?
Yes, sir.
Can I move on?
Yes, sir.
Fine.
So we could use load and count in the same terminal, right? Load / count bar. Why are we separate?
In that case,
Like
you will
most
have to.
of the places we use
Correct.
only one.
Correct. In that case, what we should do is we should connect an inverter. And for inverter, we need to have 2 connections, one from the input side and one from the output side. So instead, this is a standard IC. Okay, this is a standard IC. So they have manufactured it in such a way that count is separate, load is separate, just to null out confusions. Okay. Yes.
Yes, sir.
Can I proceed?
Yes, sir.
Okay. Right. So the next one is our 8-bit counter. Okay. So we can build an 8-bit counter with the help of 2 4-bit counters. Okay. So here we saw single 4-bit previously, and combining them, this can become a 8-bit counter. So how will it become an 8-bit counter? If we add up these values 0, 1, 2, 3, have 4 inputs here, and then 0, 1, 2, 3, 4 inputs. So 4 plus 4, 8. So this becomes an 8-bit counter. So if I want to increase the capability of my count, okay, not restricting to only 4 zeros to 4 ones, I can actually start this from 8 zeros to 8 ones. Understanding, right? So this is how we connect 2 4-bit counters. So clock is given as common, and the C out, the carry out will be the count. Okay, because the overflow, whatever overflow is there, 1 plus 1 is 0 and carry 1, right? So that carry 1, okay, whatever is our overflow, that is connected to our count. So in this way, we can actually have an 8-bit counter, and it is called synchronous because we are connecting both to a clock. Fine. The most repeated questions are these shift registers, counters which are based on shift registers. Okay. Here we have ring counter, then mod 8 twisted ring counter, and mod 7 twisted ring counter. Okay. So we will look at this one by one, and we will try and understand as to what these are. So as the name suggests, okay, now these counters are built based on the shift registers, based on the shift registers. So if you see the word here, mod 4, which means 4-bit, right? So which means whenever there is a mod 4, okay, I need 4 flip-flops, okay, 1 bit for each flip-flop, because each flip-flop is capable of holding 1 bit alone. So if I connect them in series one after the other, okay, the data just passes from here to here, from the first stage to second, second to third, third to fourth, and then finally the output is fed inside. So which means, can you tell me what is happening here? What is happening in this circuit?
So there's a feedback system.
Feedback system, and we can even call it like a ring, right? So whatever outputs are there, slowly it keeps passing, and final output is fed in. So it's like a ring. Okay, it's like a circle, just like how we saw previously. Okay, this value passes through here, and then this value passes through here, and this goes here, and this final value is fed back as a feedback, and again it comes back to our input. So which means this is a total ring. Okay, it's a total ring. Total ring. Right? So it's acting like a ring. Clocks are connected together, okay, and hence they are called synchronous. So the clocks, all the clocks are connected together, and of course, see, sometimes what we do is many modern chips do not have the Q bar, okay, because it's waste having a Q bar. Anyway, the Q bar is opposite of Q. So if you are really in need of Q bar, you can connect Q to an inverter and take out Q bar. If not, they do not want to waste resources in just building a separate pin for Q bar. Understanding now what I'm trying to say? Yes?
Q bar is not necessary, no, sir.
Yeah, that's what I'm trying to say. Q bar,
Okay.
most of the times we don't use it at all, right? So most of the modern circuitries, okay, they do not, exclusively build Q bar in their ICs, okay, in their integrated circuits. If really you are in worst case in need of Q bar, then you connect this Q to an inverter, and the output of that is considered as Q bar. Okay, so that's the concept. Why are we trying to do all this? Just to save space, just to make our ICs more compact, just to fit in few more transistors which can perform other functions, right? Just compare your calculators previously, how it was. It was so huge, performing only 4 operations, right? Addition, subtraction, multiplication, and division. But these days, your calculators are capable of even performing differentiation, capable of performing integration, right? Capable of performing matrix calculations. And just because these functions have increased, do you think your calculators have become a brick size? Is it? Has it become a brick size, and the weight has become like a
No,
brick?
sir.
Not at all, right? In fact, they have become more compact, they have become more light, they have become more efficient. Battery, I don't think so you will even change it in 5 years to 6 years, right? So they are so power efficient, okay, they are so capable, and many such things. So we do not employ these Q bar, okay, just because we do not want to increase the space and we want to reserve that space for some better functions. Okay, so this is about your
Sir, I
shift
had a
register.
doubt.
Yeah.
This counter is based on the SIPO model, sir.
Yes, serial in, serial out. Serial in, you mean serial in, parallel out? Yeah, yeah.
Yes, sir.
Yeah. We can do parallel out also because I have A, B, C, D, and there is serial in, serial out. If I take from here, it is serial in, serial out. Right. From this
So it
point.
is either of the models.
So either it can be serial in, serial out, or it can be serial in, parallel out. But here, since we are talking about ring, so ultimately we wouldn't take outputs from A, B, C, D. This is just kept for your reference. Okay, that you can tap into these values at any point of time. D value you can tap, B value you can tap and access, A value you can tap and access. So you can have a look at the table, okay, truth table, which is towards the right hand side, and you can check that, you know, suppose I give 1, okay, suppose initially I feed 1, okay, so that keeps passing through, 1 keeps passing through, and you can see that, you know, it is in this fashion. The 1 keeps passing through. Then again, this D is fed back to whom? It is fed back to QA. Okay. So again, this cycle repeats. Okay. So that is what you can see here. After this state, after the clock pulse, this will be passed on and it will come to QA. So which means it is referring to our first state. After the first state, then again, it continues with the next state. Any doubts with this as to how we have got these values, how these values are passing by? Any doubts?
No, sir.
Okay, fine. So the property of this, okay, since the values are going, okay, one after the other, and the feedback is given back to the input, so it is termed as a ring counter. Okay, so it is not that efficient in number of flip-flops used, but it provides a decoded output. To detect any particular state in the counting sequence, it is only necessary to interrogate the output of a single flip-flop. So if in case, as I mentioned, you want to check the values at any point of time, okay, these tap points are available, okay, these access points are available. So through these access points, you can find out if properly you're getting values at D flip-flop, sorry, at the 4th flip-flop, at C flip-flop, okay, then at B flip-flop or at A flip-flop. So if there is any discrepancy, then we can look after only that particular flip-flop and we can find out the errors and we can start rectifying it. Okay, so that's the reason why these points are given. So can I move on? Shall we move to the next topic?
Yes, sir.
Fine. So the next application that we'll be looking into is twisted ring counter. So the only difference here is, can someone tell me what is the only difference here? Same D flip-flops, same clocks, common clocks, ABCD is there. What is the only difference?
We
The
take
final
feedback.
output is taken from Q complement.
Q bar is taken instead of Q, right? So that's why it's called twisted ring counter. Okay, fine. So this is capable of actually giving us the complemented output. So in order to get the full state, okay, in order for me to get all zeros, it will take double the number of values. So when I say double, if it's 4, then it should take me 8 states, okay, to get back to my initial state, right? So now let us see the values that are here, okay. So initially if I feed 0 0 0 0, okay, that is my initial value. So what is going to happen is 1 QD is 0, okay, so QD bar becomes 1, okay, so that is here actually, you can see, okay, 1, and this 0 is pushed, okay, this 0 is pushed here, and then this 0 becomes 1, it comes. So as you can see, it keeps passing by, okay, it keeps passing by. So at one point of time, okay, this 0 here becomes what? It becomes 1 in the next state, okay, because the complement of 0 is what? 1, okay, and this 1 which was here will go this side. So it is just a one bit right circular shift, right circular shift, 1 bit, okay. So this 1 will again become 0, and then it will come here, this 1 gets pushed, and it, instead of first bit, it will go to the second bit. Second bit means what? From A, it is going to B, right? So it keeps going on, and by the time I get my initial value, which is 0, okay, so by the time I get my initial value, it will take me 8 states, 1 2 3 4 5 6 7 8, 8 states, okay. So that's why it is called mod 8 twisted ring counter. Any doubts here? Students, any doubts here?
No, sir.
Okay, fine. So only thing that you have to see here is how these values are going through, okay. So initially say it was let me just put those values, that becomes easy. Yeah, so initially say it was 0 0 0 0, so which means I'm getting 0 here, but here it's going to be 1, right? So this 1 will come here, and this 0 will get pushed to the next flip-flop, and this 0 will get pushed to the next flip-flop. This 0 will come here to the next flip-flop, right? So at every positive cycle of your clock, okay, these values keep shifting from one to the other. Right. So it is also called switch tail counter or Johnson counter. Sometimes to confuse you, there are 3 names: switch tail counter, Johnson counter, mod 8 twisted counter. 3 different names for the same functionality. Okay, so don't get confused. Switch tail, Johnson, twisted ring counter. The complement of the rightmost flip-flop serves as input to the leftmost flip-flop. Yes, we have seen that. 2 n states occur in counting sequence of n stage counter. So even though it is 4 stage, but still we need 8 stages because the complement takes time to get back to its original state. Okay, so normally it is 2n. So if it's 4, then 8 states. If it's 5, then 10 states. Underlined pairs of bits uniquely determine a state. Okay, so you can see the underlines here. So which means those which are actually changing. Okay, this is the feedback that comes through. A single 2 input and gate is required to obtain a decoded output. So if in case you want an decoded output here, you need to have a 2 input AND gate. Okay, so is required to obtain the decoded. Always have even number of states. So it's always nice to have even number of states, like 8, 16, 32, like that, even number of states. Fine. So the next one, based on counters with the help of shift registers, is your mod 7 twisted ring counter. Okay, mod 7 twisted ring counter. So with this, can you tell me what is happening? What's happening here in this circuit? Yes, sir, you all
So
there?
an AND gate is present.
And it is present, and I'm not only just taking the final state, but I'm also taking the previous state, okay, and checking their values. Okay, whatever is the values, either I get 1 1, then 1 will be fed, either I get 0 0, then 0 will be fed. Okay, so by this, what I can do, I can have for odd number of states. So for the previous one, it was even number of states, right? That was good for even number of states. Now if I employ an AND gate here, this will work out for our odd number of states. So just look at these, the same concept. Okay, D comes through, so which means D bar, which means 1 and 0, it passes through, it keeps passing. Okay, and at one point, it is going to check, for these values. Okay, so suppose if it is a 0, okay, let us say now we have to concentrate on both C and D. Okay, values of C and D. So if C and D is 0, okay, if C and D both the values are 0, then 0 is going to be fed in. Now here we are seeing the true values, not the complemented values. Okay, so which means whenever it is 0 0, it means our Q and Q bar, okay, our Q bar of, or specifically if I have to say QC bar and QD bar are 1. Okay, so you can see that, okay, 1 is passing through, 1 is passing through. If in case, okay, if in case there is a 1 1, okay, if there is a 1 1, let's say this state, okay, 1 1, so here also what is going to happen, it is going to check um, the Q bar value. So Q bar value, which means 0, and anything into 0 is actually 0, so 0 will come and sit here in our first flip-flop. Okay, so this is used for our mod 7 twisted ring counter. The same concept, just that we have to take bit by bit and consider how it is passing. So this is called our twisted ring counter for odd number of states. And the state consisting of all ones is eliminated from the counting sequence. Why is it eliminated? Because of the AND gate, right? Because of the AND gate. So if you can see here, okay, all ones is not available. So that is the only state which has been eliminated. Okay, because if it is 1 here, what is going to happen? 1 and 1. I'm going to get 0 and 0 here, right? Just see, if my output is 1 here, output is 1 here, I'm going to get 0, I'm going to get 0. Okay, so 0 into 0 is 0. So 0 will come here, it will come and sit here. So which means it will never allow for all ones. It will never allow for all ones. So this state is eliminated. Apart from this, I have everything. Okay, I have all the other states. So that's why it is 8 states minus this all high state. So it becomes my mod 7 twisted ring counter. This logic design is like this, it's like a game. You can keep playing around with the logical gates. You can keep playing around with the connections and so on, right? So this is achieved by connecting QC bar and QD bar to the input of the leftmost D flip-flop, leftmost, which means the first flip-flop. Each state is detectable by the use of single 2 input and gate. So students, any doubts that we have discussed so far?
So can this also be referred as the Johnson counter?
This is called mod 7 twisted ring counter, mod 7. This is not Johnson counter. The previous one is Johnson for even number of states. Taking Q bar, the last Q bar. Okay.
Fine, sir.
Okay. Fine then. So we will stop here and we will continue with our next topics in our upcoming classes. Okay. Thank you.